All right, so let's talk about writing the electron configuration for ions. So we've talked about writing just the typical electron configuration. For ions, it looks a little bit different depending on what you're talking about. So real quick, let's review. Positively charged ions are called, wait for it, cations, and negatively charged ions would be called anions, okay? Non-metals are typically going to gain electrons to form anions, so negatively charged ions. So again, those we've covered that before, but those are important concepts for you to be able to talk about what it is that we're going to do, okay? So your nonmetals are on the right side of the periodic table. They're usually going to gain electrons. Your metals are on the left side, and they're usually going to lose electrons to form cations, okay? Okay, so when we write electron configurations, remember those valence electrons are those outer shell things. And for our main group elements, we're usually going to have, so if it is a full, so those noble gases are going to typically have valence electrons that are equal to 8, okay? Usually this is where we want to go. So when ions form, they usually want a full shell, okay? Whatever that looks like, that's where they want to go. And usually we're going to have things that we call isoelectronic elements. And that's when you have elements that all form ions that look the same. So for example, phosphorus, the phosphide ion, sulfide, chloride, argon, potassium, calcium, these are all isoelectronic because they form ions other than argon. Argon is the noble gas, that's where they want to be. They either gain or lose electrons to form a full shell. Okay, so total they're isoelectronic because they have the same number of electrons. They all have 18 electrons. So for example, potassium has 19 electrons by itself, but when it loses an electron, it becomes 18. Calcium usually has 20, it loses 2 to become 18. Sulfur has 16, it gains 2 to become 18. Chlorine has 17, it gains 1 to become 18, and argon would be right there. Okay. The octet rule, we'll talk a lot more about this when we get to the next unit, but essentially it says, hey, things are going to either gain or lose or share electrons in order to have an octet, 8 things. And so that is the rule that drives a lot of these ion formations, okay? There are exceptions. We'll talk more about these when we get to bonds and things like that. And that's typically a duet. They'll usually form 2, sometimes 4. But usually most things are going to form 8, gain or lose or share electrons to get 8 or 2. Okay. So for example, here's how potassium chloride, again, we'll talk more about this later, but this is what this would look like. But here's what the typical potassium element electron configuration is. It's going to lose an electron right here to form the ion. And so that goes away, and now we have a full shell. Okay. In general, your group 1s, all the A's, right, are going to lose and gain from their outermost shell. So usually the two. So for example, this would lose from its outermost shell. These will gain to their outermost shell. Same hold true for all of these things, okay? In general, group 1 will form +1 ions because they're losing 1 electron. Group 2 will form +2 because they're losing 2. Group 3 +3 because they're losing 3. Group 5 will form -3 because it's gaining 3 electrons. Group 6 -2, and so on. Again, everybody wants to look like the cool kids who happen to be, in this case, the happen to be the what's the word? Noble gases. Okay, so that's where we're going. That's what we want to do in this case. Okay, hold on, let me share my screen again to get where we need to get to. So that's how these ions would form. Again, losing from the outermost shell. Okay, so for example, sodium right here is going to lose that to form the sodium ion. Fluorine right here is going to gain 1 to form the fluoride ion, okay? For group A, so group 1A, 2A, 3A, 4A, 5A, 6A, 7A, they will always gain or lose in the outermost shell, usually the S or the P orbitals. Okay, that's where that's gonna happen. Transition metals though, okay? So they fill in terms of energy order for transition elements, your D is usually going to be higher energy than your S orbital, even though the N levels are a little bit different. So this I cannot overemphasize. I will mention this again when I see you in class. Loss of electrons for transition elements, you always lose from the S orbital before the D. Always, 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 no exceptions. This is how this happens for transition elements, okay? Again, we lose from whatever has the bigger N, even though technically the D orbital will have higher energy than the S orbital. We will lose first from the S orbital, okay? Because based on, by definition, a lot of the transition elements actually have multiple ions, we can lose multiple types of electrons. We can lose electrons multiple times, okay? So for the group A elements, they're usually looking to be like the closest noble gases. For transition metals, they don't care. They just lose and gain, by themselves. Okay. Again, transition elements will always lose from the S orbital or S block first before they lose from the D block. Okay. So for example, silver, the silver ion, you lose this electron first. Iron, remember, we can form two ions. If I lose one here, I lose two here to give me that, but I could also lose an extra one to form iron 3, and that's why I have that over here. Titanium has two ions, and so lose all of that to give you that. Or I could also lose that to just have, now I have a argon. I look like a noble gas, but that doesn't have to be what they're looking for. Okay. Again, remember your transition elements can have more than one state with these exceptions. If you think back to when we were naming, we looked at those, but yeah, transition elements will usually lose multiple electrons because they can have multiple states. All right, let's talk about paramagnetism versus dimagnetism. So this idea of ions and filling up electrons, orbitals and things like that is actually going to can result in different types of magnetizations. Okay, so if you have stuff with unpaired electrons, that means if I have my orbital block and I have these are what we call unpaired electrons, and these would be paired electrons. Okay, so these are paired, these are unpaired. So in order for you to determine whether you have magnetization, so paramagnetism versus dimagnetism, you need to know what the electron structure looks like, electron configuration. Paramagnetism, unpaired, and this is attracted to the magnetic field. Diamagnetism is paired and it is actually repelled by a magnetic field. Okay, so here are fair questions. I could ask you, hey, which of these are paramagnetic? So unpaired versus diamagnetic, which is paired. In order for you to figure out this question, you have to write out the electron configurations for them. Okay, so take a little bit of time, write it out by yourself. Here's what that looks like. And I have done this ahead of time. And essentially, this is paramagnetic, it's unpaired, diamagnetic, paired, diamagnetic because it's paired, again, unpaired, pair. Okay, so that's how you would figure out magnetism versus non-magnetism. And that's it.